So in this video, we're going to look at calculating confidence intervals for correlations. And if you're not too familiar with confidence intervals or the standard error or the z-score associated with various limits of confidence intervals, you might be better off just checking out these really short videos first. Okay, in our example, we have a correlation coefficient of 0.6. Now that's going to produce a distribution that looks like this. So there's 0.6, and because the highest value you can get for a correlation is 1, you can see it's really skewed. But in order to calculate confidence intervals, we need to be working with normally distributed data. So we have to run this all through Fisher's Z, which is a formula that looks like this. So Fisher's Z is calculated as 0.5 times the natural log of 1 plus the correlation coefficient divided by 1 minus the correlation coefficient. But what's great is that Excel has the formula built in, and we just need to type in equals Fisher and then highlight the relevant cell that contains the correlation coefficient we want to transform. So we now have our z-score for our correlation. Now the next stage in order for us to calculate our confidence intervals is to determine the standard error. So the standard error is like the standard deviation, but it's going to tell us how far our sample deviates from the population. And obviously the larger the sample, the more closely it resembles the actual population. So the value will start to get smaller. And I can just illustrate that here. So we're working with a sample of 16. If I increase that value to say 30, then the standard error should start to drop. And if I skyrocket our sample up to 100, you can see that the standard error drops again. And if we happen to be working with a really small sample size of just 8, then that standard error now shoots up and is really high. And again, another example of why your sample size is so important to the power of your statistics. So the standard error in this example, where we're calculating confidence intervals based on correlations, is 1 divided by the square root of the sample size minus 3. So we now need to multiply the standard error by the z-score of whatever confidence limits we want to work with or capture. And by convention, we use 95% confidence intervals. And that's associated with a z-score of 1.96. Now, I like 90% confidence intervals, which is a z-score of 1.64, or you could change it to 99% if you really wanted to capture a large part of the population, but the z-score is really going to shoot up. And I put in a formula here such that we can sort of go off piste and calculate whatever confidence interval we wanted. And the formula here is the inverse of the normal distribution. And you can see, you can just type that in and just type the probability value in. So if we were working with 95% confidence intervals, the probability value associated with that is 0.05. So all I've done is manipulate this so that when you use this number, you'll then get 0.05. Or if you type in 90% confidence intervals, you'll get 0.1, 99% confidence intervals, you'll get 0.01, and so on. Now, we're going to calculate the lower limit for the z-score, and that is quite simply calculated as our z-score for our transformed z-score from the RR value minus the standard error multiplied by our z-score of choice, which in this case, if we're working with 95% confidence intervals, is 1.96. And then we just do exactly the same for the upper limit, with the exception that we now add the standard error multiplied by the relevant z-score. Now, the final stage is just to convert it all back from a z-score into a correlation coefficient. And again, that's great because we can use the formula equals Fisher inverse, and again highlight the relevant cell. So we can do the same over here. And now we get our limits. And so what we can do now with this data is that we can act as though the true population value lies within these limits. And I've also illustrated that here below, because typically within our data we always focus in on the point estimate. And the idea behind confidence intervals is that it gets you to appreciate the limits of the data, and that all values that are within these limits are compatible with your data. So you therefore going to have a little bit of more humility when you interpret your results. And of course, as you change the correlation here, you can see it changes the values here as it does throughout the whole sheet. So you can download this sheet from Researchgate, and if you look within this project here under project log, you can grab it here, but I'll put the link under the video.